Hello students, today we are going to study in Science-1 Chapter 2 Periodic Classification of Elements Part 2. The scientific world did not know anything about the interior of the atom when Mendeleev put forth the periodic table. After the discovery of electron, scientists started exploring the relation between the electron number of an atom and the atomic number. The atomic number in Mendeleev's periodic table only indicated the serial number of the element. In 1930 AD, the English scientist Henry Moseley demonstrated with the help of the experiment done using X-ray tube that the atomic number of an element corresponds to the positive charge on the nucleus or the number of the protons in the nucleus of the atom of that element. This revealed that atomic number is a more fundamental property of an element than its atomic mass. Accordingly, the statement of the modern periodic law was stated as follows. In the modern periodic table, elements are arranged in the increasing order of the atomic number in the form of a table having 7 horizontal rows of elements called periods and 18 vertical rows of elements called groups. The statement of the modern periodic law was stated as follows. Properties of elements are a periodic function of their atomic numbers. In other words, when the elements are arranged in order of increasing atomic number, elements with similar properties appear at regular intervals. In the modern periodic table, the elements are arranged in accordance with the atomic number. As a result, most of the drawbacks of Mendeleev's periodic table appear to be removed. However, the confusion or the ambiguity about the position of hydrogen is not removed even in the modern periodic table. Now we shall see the structure of the modern periodic table. The modern periodic table contains 7 horizontal rows called the periods 1 to 7. Similarly, the 18 vertical columns in this table are the groups 1 to 18. The arrangement of the periods and the group results into formation of boxes. Atomic numbers are serially indicated in the upper part of these boxes. Each box corresponds to the place of one element. Apart from this 7 rows, 2 rows are shown separately as you can see at the bottom of the periodic table. These are called lanthanide series and actinide series respectively. So altogether there are 118 boxes in the periodic table including 2 series. It means that there are 118 places for elements in the modern periodic table. All the 100 elements are now discovered. The entire periodic table is divided into 4 blocks: S block, P block, D block and F block. The S block contains the groups 1 and 2, while the 13 to 18 constitute the P block. The groups 3 to 12 constitute the D block, while the lanthanide and actinide series at the bottom form the F block. The D block elements are called transition elements. A zigzag line can be drawn in the P block of the periodic table. The 3 traditional types of elements can be clearly shown in the modern periodic table with the help of this zigzag line. The metalloid elements lie along the border of this zigzag line. All the elements lie on the left side of the zigzag line, while all the non-metals lie on the right hand side. Now we shall see modern table and electronic configuration. You will find that the number of valence electrons in all these elements formed from the group 1, that is the family of alkali metal, is the same. Similarly, if you look at the elements from any other group, you will find that number of the valence electrons to be the same. For example, the elements beryllium, magnesium and calcium belong to the group 2, that is the family of alkaline earth metals. There are 2 electrons in the outermost shell. There are 7 electrons in the outermost shell of the halogens. While going from top to bottom within any group, 1 electronic shell gets added at a time. As you can see in this picture, from this we can see that the electronic configuration of the outermost shell is the characteristic of a particular group. So as we go down a group, the number of shells goes on increasing. And that while going from left to right within the period, the atomic number increases by 1 at a time, and the number of valence electrons also increases by 1 at a time. So we can say that the elements with the same number of shells occupied by electrons belong to the same period. The elements in the second period, namely lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, have electrons in the 2 shells, that's K and L. The elements in the third group, namely sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon, have electrons in the 3 shells K, L, M, and so on. Next we shall see about valency. Now what's valency? Valency of an element depends upon the number of valence electrons present in the outermost shell of its atom. So we can define valency as combining capacity of an atom of an element with atom of another element to obtain the octet structure. So you can see that valency of elements present in group 1 will be 1, group 1 and 17 will be 1. Valency of elements present in group 2 and 16 will be 2. Valency of elements present in group 18 will be 0. Valency of elements present in group 13 will be 3. As you can see, so the trend in the periodic table, the valence electron are also the factors that determine the chemical properties of an element. So you can see that along a period, the valency increases from 1 to 4 and then it decreases to 0 as we reach rare gases. Within a group, the valency of elements remains the same. So you can see from the table, the first period has got 1 shell, second period has got 2 shells, third period has got 3 shells, fourth period has got 4 shells. Similarly, in group, when you moved along a group, you can see that in the first group, 1 electron is present in the outermost shell. Group 2 has got 2 electrons. Group 3 has got 3. Group 4 has got 4, and so on. Next we shall see what's atomic size. The size of an atom is indicated by its radius. Atomic radius is the distance between the nucleus of the atom and its outermost shell. Atomic radius is expressed in the unit picometer, which is smaller than nanometer. Some elements and the atomic radius are given as oxygen 66, boron 88, carbon 77, etc. Now if you see in the table, you will find that atomic radius goes on decreasing while going from left to right within a period. That's because while going from left to right within a period, the atomic number increases 1 by 1, meaning the positive charge on the nucleus increases by 1 unit at a time. However, the additional electron gets added to the same outermost shell. Due to the increased nuclear charge, the electrons are pulled towards the nucleus to a greater extent thereby the size of the atom decreases. You will find that while going down a group, the atomic size goes on increases. This is because while going down a group, a new shell is added. Therefore, the distance between the outermost electron and the nucleus goes on increasing. As a result of this, the atomic size increases in spite of the increased nuclear charge. Next, we shall see metallic and non-metallic character. Now, as we had already seen in the periodic table, that zigzag line separates the metals from non-metals in the periodic table. Elements appear to have arranged in such a way that metals are on the left-hand side of this line, non-metals on the right-hand side, and metallites are along the border of this line. Now let's compare the characteristic chemical properties of metals and non-metals. Metal atoms have a tendency to form a cation by losing its valence electron. This property is called electropositivity of an element. On the other hand, an atom of a non-metal has a tendency to form an anion by accepting electrons from outside into its valence shell. Electrons in the inner shell lie in between the valence shell and the nucleus. So, because of the presence of the effective nuclear charge exerting on and exert attractive force on the valence electron is somewhat less than the actual nuclear charge. Thus, the number of valence electrons in metals is small. Also, the effective nuclear charge exerting attractive force on the valence electron is small. As a combined effect of these two factors, metals have a tendency to lose valence electrons to form cations having a stable noble gas configuration. This tendency of an element is called electropositivity, that is, the metallic character of that element. While going down a group, a new shell gets added, resulting in an increase in the distance between the nucleus and the valence electrons. This results in lowering the effective nuclear charge and thereby lowering the attractive force on the valence electron. As a result of this, the tendency of the atom to lose electron increases, and due to this, the tendency of an atom to lose electron increases further. The metallic character of an atom is its tendency to lose electrons. Therefore, the following trend is observed, that the metallic character of elements increases while going down the group. While going from left to right within a period, the outermost shell remains the same as we have already seen earlier. However, the positive charge on the nucleus goes on increasing while the atomic radius goes on decreasing, and thus the effective nuclear charge goes on increasing. As a result of this, the tendency of an atom to lose valence electron decreases within a period from left to right. These two factors, namely the increasing nuclear charge and decreasing atomic radius as we go from left to right within a period, are responsible for increasing the effective nuclear charge. Therefore, the valence electrons are held with greater and greater attractive force, and this is called electronegativity of an atom. Due to increasing electronegativity from left to right within a period, the ability of an atom to become anion by accepting outside electron goes on increasing, and the tendency of an element to form anion or electronegativity is the non-metallic character of an element.